So I just put it to record. Is there something you wanted to? Pardon me? Is there something you wanted to double check on it? I just set it to record.
Oh, no, it's flashing. I just wanted, last night Mohammed gave me the password to the upgraded one. So now we have 25 streams.
If there's ever an exercise that I don't know how to
I'm working on the database. But
yeah, the extra credit is really silly.
This works for me.
What I noticed for me, the mic works better if it's a little bit sideways because you work differently. I move my head up and down.
Oh, you might as well do it.
It's a big difference.
It's extra credit, right?
So some people I know see it and they have it actually.
Oh, really?
Once you read the exercise,
Maybe I'll try playing with it a little bit.
solution pretty quickly.
Yeah, should be good.
The thing is, it's so easy, but that construction is something that's going to come up kind of again later. If you have that example in the back of your head, even though it seems really easy now, it might help make something more clear later.
Okay.
I just wanted to start by making a small correction to something I said when I was defining spanning trees of a graph. So let's assume G is a connected graph. And I said a spanning tree was a subgraph which is connected and has no cycles. And there's a third condition that I was careless and forgot to write down, and some Jeff Doker corrected this for me on the forum. Which is that this subgraph has to reach every vertex. Okay. So this subgraph contains every vertex of the graph.
Isn't that embedded in saying it's connected, though? If you have the same vertices?
So I think probably you understood me quite well what a spanning tree is. A spanning tree is what you think it is. But what I said is not quite correct. When I wrote the definition, it wasn't quite correct because in the previous definition that I had, you could just take this subgraph consisting of these three vertices and these two edges. Well, that subgraph is connected and it has no cycles. But you certainly wouldn't want to call this a spanning tree. A spanning tree should span the whole graph, and that's why it's called spanning. And so a spanning tree is something like this. That's a spanning tree. Okay. So I don't think people were really confused about that, but I want you to have the right definition on the notes. Okay?
Because by definition of a subgraph, it doesn't have to have all the vertices.
A subgraph does not necessarily include all the vertices. That's right. Now, the first thing that I want to do today is something that I've never found a proper word in English for this. In fact, I don't think this quite translates. Cultura general. So this is something in Spanish, which essentially means something like whatever cultured people are supposed to know. So the kind of thing that they might ask you in a crossword puzzle, like, what's the capital of Venezuela? This is general culture. Conventional wisdom is close. It's not quite the same thing. But cultura general, things that a student of combinatorics should know. Cultura general in algebraic combinatorics. And you might have heard in the past something called algebraic combinatorics. And you might have wondered what this algebraic combinatoric business is about. I mean, people dedicate their whole research to algebraic combinatorics, and I want to start by showing you a theorem in algebraic combinatorics. Okay? let's say that I give you a graph. So, for example, here's a graph. And I ask you, how many spanning trees does this graph have? So question, how many spanning trees? Does my graph have? Let's assume that the graph is connected so that it actually has spanning trees. Okay. So if I were to ask you this question for this graph, then you could definitely just do it manually. Just draw all the possible spanning trees and you could do it. But if I give you a very, very large graph, then you do not want to do that. You want a better method than to have to make the list manually. Okay? This is exactly the kind of question that combinatorics or enumerative combinatorics talks about. You want to know how many things there are, but you don't want to go through all of them. You want a better method. Okay? So I'm going to show you how to answer this question. Let's call this my graph V, comma, E. Okay. Maybe I'll label the vertices A, B, C, and D. Okay? So now what I'm going to ask you to do is to form a matrix. So we're going to form a matrix, and it's going to be a square matrix of size the number of vertices. So for example, here I need to be building a 4x4 matrix where the rows and the columns are labeled by the vertices. Okay? I'm going to put numbers in this matrix, and I'll tell you what number you're going to put. So first of all, I'll tell you what to put in the diagonal. In the diagonal entries, you're just going to put the degree of each vertex. Degree meaning the number of edges coming out of there. So for example, if you want to know what the entry A, comma A is, then you just count how many edges go out of that vertex. 1 and 2. So that's the A entry. The BB entry, there's 3 edges here, so I put a 3 here. The CC entry, there's 3 edges coming out of vertex C, so I put a 3 here. And for the DD entry, there's 2 edges coming out, and so I put 2. So this is the degree of my vertex B, number of edges containing it. Okay. So that's what I put in the main diagonal. And then outside of the diagonal, in entry U, comma V, I'm just going to say whether there are edges or not. Okay? So for example, if you want to know what the entry A, comma B is, then you're going to see, is there an edge between A and B? Well, there is. And I want you to record not a 1, but a negative 1. Okay? So you're just going to put the negative of the number of edges there are. There's 1 edge between A and B, so you put negative 1. Between A and C, there's 1 edge, so you put a negative 1 here. And between A and D, there are no edges, and so you put a 0 here. Okay? Of course, this matrix is symmetric because then there is an edge between A and B if and only if there's an edge between B and A. So I can put -1, -1, 0. Between B and C, there is an edge, so I put a negative 1. Between B and D, there is an edge, so I put a negative 1. And between C and D, there's an edge, so I put a negative 1, and that's my matrix. Okay?
So if you happen to have 2 edges between the same vertices, you put -2? If you had,
right, so in fact, let me change my example on you. So that let me add another edge here between B and C. So how does that change things here? Well, you have to change the degrees of B and C. Right? So now out of B and C, you have 4 edges. And between B and C, I don't have 1 edge anymore. I have 2. So I have to change the entry BC, which is this one, and the entry CB, which is this one. And instead of -1, I'm going to put -2. Question here on this?
Cash, how did you get the B and the H thing? What is it for H?
Where did I get this for? Because my first condition tells me that the number I should put on the diagonal, B, comma B, should be how many edges are coming out of vertex B. And there's 4 of them.
Can I have another question?
Yeah?
Why do you choose -1? Why don't you use say 1?
For my theorem to work. I haven't told you what the theorem is. But the theorem wants a negative there.
Okay, thanks.
So this is called the Laplacian of the graph. Oh, so LUV is minus the number of edges between U and V, which might be 0. Okay. This is called the Laplacian matrix of the graph. Okay. And you should be wondering why on earth I'm doing this. This is a very relevant question. Why do I put minus? Why do I make this matrix? The reason I do it is because this matrix is going to answer that question. Okay. So the answer to my question, how many spanning trees does a connected graph have? This is the answer. Just compute any cofactor of this matrix, and that's the answer. The number of spanning trees of the graph equals any cofactor of its Laplacian. What is a cofactor? Maybe you remember, maybe you don't. In a cofactor, what you do is that you remove a row, remove a column, and compute that determinant. Okay? And so I'm going to ask you guys to do it. So each one of you is going to choose whichever row you want to choose whichever column you want to choose, and compute the determinant. Okay? If this theorem makes any sense, then we better get the same answer, all of us. So for example, I'm going to maybe delete this row and this column, and I'll compute this determinant, but you guys should pick different ones. So does anybody want to yell out what answer they got? Shortly. So someone got a 12.
Yeah, I got a 12. Minus
You got a 12 also? You got a minus 12?
4, yeah.
Is anybody worried about this minus sign? So I think everybody should get a 12 or a minus 12. No, so some of you should get a 12 and you didn't make any mistakes. And some of you should get a negative 12 and you didn't get any mistakes. But the problem is that there's one missing thing in the definition of cofactor, which is that cofactors have signs. And the sign that you're supposed to put is negative 1 to the I plus j. So for example, here, I is 2, j is 3, and so I should have a sign of negative 1 to the 5th. So I should have a minus sign in front of this guy. And so my answer is 12. Now, depending on which row and column you pick, you either get a minus sign or a plus sign, but you get one or the other. And so, Miranda, this is the answer to your question. If you put pluses, the theorem is not true. And you want a theorem that is true because you want to compute this number. Why is this called algebraic combinatorics? Because I started with a counting question. And you should be very surprised if this is the first time you see a theorem like this. You should have no idea why you can compute a determinant and get the right answer. It's the kind of thing where you know, it happens very often in combinatorics that you need algebraic techniques to count simple things like this one. Okay? So this is known as Kirchhoff's theorem. Make sure that I spell this correctly. This is the same Kirchhoff as in the Kirchhoff laws of electricity. Okay, and we won't do a proof because this isn't really a theorem about matroids. This is really a theorem in algebraic combinatorics. But a possible project that I think you guys could consider, a final project that you could consider, is to understand this. Understand this theorem and it turns out that this is a theorem that tells you how many bases a graph has. Okay? But this generalizes to a theorem about not graphical matroids, but linear matroids. So a final project that you might consider doing is understand this theorem and its generalization to linear matroids. So this is well suited for whoever has more of an algebraic interest. So this is should really be an algebra project more than anything. Any questions about Kirchhoff's theorem? Actually, this theorem has a name. So this is called the matrix tree theorem. Matrix tree theorem, and it's due to Kirchhoff. So that's my little parenthesis. And that's a possible final project that I offer it to you guys, and I'll be happy to point you to the right places to read about this stuff. Okay. So this is a little parenthesis, and let's go back to a more matrix theoretic question. But in fact, what I want to do is start right away with a real-life application of matroids. A real-life problem. So let's say that you have a graph that represents maybe a country. So there's my country. Each one of the vertices is a city. Each one of the edges is a possible road that you are considering building. Okay? And you maybe did some research ahead of time and you figured out how much it would cost to build each one of these roads. So to connect these two cities would cost you, I have no idea how much building a road costs. $100,000? I have no idea. Let's say 1 unit. 2. So each edge has a cost. And of course, what I want you to think about is, how do you connect these cities? You want to build a road system so that you want to build a road system that connects all the cities. Okay? And of course, you're a cheap government and you want to do this as cheaply as possible. So goal. So you don't care if to go from this town to this town, you make the person drive around the whole country and come back. All you care is that they're connected. Okay? So goal is to find road system. Not find, because you're not going to find it. You're going to build it. Build a road system that connects every city. That connects all cities for the smallest cost possible. For the minimal possible cost.
What are the numbers, the distances between the cities?
The numbers represent the cost of what it might be. So you're probably asking me because of this 17. So maybe there's a canyon here, and that's why it's ridiculously expensive to build over that canyon. Okay. Now, of course, this is maybe not realistic. A government wouldn't make you want to go all the way around. But maybe if you think about this as a computer network, for example, and you think about this as an internet network, the internet is fast enough that if you have a good connection, you don't care if you go around. That's not going to be so much slower. So this is really a question that people wonder about. And of course, we can translate this into, what are you trying to build here? You want to connect every possible city to every other one. You don't want cycles because that would be superfluous. So closing a cycle is unnecessary because you just want to connect everybody. And you want to reach every vertex. So what you want to do is build a spanning tree. In other words, this is find a minimum weight spanning tree. This is the goal, what you want to do. Okay. So if you were a very, very short-sighted government, which many are, what is the first thing you might do?
Start going along and pick the cheapest way at each point.
To say, oh, look, this is kind of cheap, mate. Let me start with that. Okay. So maybe my government says, well, the cheapest possible road is this one, so let me just build it. Why not? So maybe the government decides that it wants to build this road right here. After that, then it says, okay, well, this one's pretty cheap too, so let me build that one. So it builds this one. And then it says, okay, the next cheapest road is this one right here. So I build it. The next one is this one right here. So I build it. The next one is this 3. Do I build it? No, right? Because I already know how to go around here. I don't need to build this one. Okay? But I will build this 3 because that's useful. Then the next ones are worth 4, so I don't build this one because I can already go around, but I should build this one, and I don't build this one. Okay? So the next cheapest one is this 7, so I build that one. Then the next cheapest one is 8, and 8. And I think I'm done, right? Yeah. So what is the naive strategy that this government is following is do the cheapest thing possible at any point in time. this is something called known as a greedy algorithm. Greedy algorithm. It just says, at each stage, just do whatever you think seems best at the time. At each stage, build the cheapest road that doesn't form a cycle. Okay. This is what's known as a greedy algorithm. And again, greedy is not too common of a word, and so I want to translate it to Spanish. So for the Spanish speakers, the way people translated this to Spanish is something called algoritmo voraz. You say that an animal is voraz if it eats everything around. I think that word probably exists in English also, voracious. Yeah. Or other people call it algoritmo glotón, the glutton algorithm. And it just okay. So that's the greedy algorithm. And now, do you expect this to work? Well, the only reason you might expect it to work is because I'm talking about it. But this really shouldn't seem to you like a good strategy necessarily. It's not clear that this should work. Okay. But the fact is that it does. Okay. So a theorem, this works. I'll say exactly what I mean by that. But again, I want to emphasize to you this theorem is due to Kruskal in 1956. Okay. But what I want to show to you is that this is not graph theory. This is matroid theory. This is really a theorem about matroids and not a theorem about graphs. Okay. So let's generalize this problem to the setting of matroids. Okay. So let's say that I give you a matroid. And just like here, I give you a weight on each edge. Here, I should give you a weight on each element of the matrix. So for each element of the matroid, I'm going to assign some positive weight. Okay. So it costs you something to grab this element of the matroid. Okay. And the problem is to find a basis, just like here a spanning tree. Find a basis of minimum weight. Okay.
So technically then you're assigning another map from the power set of E to R to be the sum of its weights.
That's right. So I guess I should write that down explicitly. What do I mean by the weight of a basis? Yeah. I mean the sum of the weights of the elements. The weight of a basis. Let's say B is consisting of E1 up to ER is simply the sum. Cost of the first element, so on, until the cost of the last element. So given a matroid, I'm asking you to find a basis of minimum weight. And we're going to figure out what a greedy algorithm would be in this case. I should mention to you that the word greedy algorithm appears all over theoretical computer science, and it doesn't just refer to this problem. A greedy algorithm is a general strategy that says, at each point, do the thing that seems right locally. Do the optimal thing that you can do right now. And hope that if at each point in time you're doing the right thing, then hopefully, in the end, you will have the optimal solution. It doesn't always work, but this is something called the greedy strategy, the greedy algorithm. So what is the greedy algorithm for a matroid? The greedy algorithm for this problem. Well, what you're going to do is, first you're going to start with the empty set. Okay? And you're going to start adding elements to it. At each point, you're going to add to I an element E of minimal weight so again, you do exactly the same thing that we did over there. You look around, look for the cheapest thing, and you add it. Unless what? In that case, I added it as long as it didn't have a cycle.
Yes, unless
I'm trying to build a basis, and so I better stay independent. So I add to I this element E as long as I'm still independent. As long as adding it still gives you an independent set. Okay. And you keep doing this until you're done. You repeat step 2 until you get a basis. Okay. That is the greedy algorithm. Okay. And so, theorem. The greedy algorithm works for the problem of finding a minimum weight basis of a matroid. Theorem, the greedy algorithm, finds a basis of the matroid of minimum weight.
Efficiency doesn't seem like it seems a pretty practical term.
Yeah, I agree that probably if I had asked you to give this a name, you would have called it a cost function, not a weight function. And I think this is what you mean. In matroid theory, people like to call these weights, and you might think of the lightest basis or something like this. But the weight is a very general term that might mean cost, it might mean efficiency, it might mean whatever it means. But as long as this notion of weight that you're studying is living in a matroid and it is an additive notion, if the weight of a basis is the sum of the weights of the elements.
I was thinking like, say, like the smallest length of the vectors or something that, that you would be picking. If you just had like, a matroid that, in vector configuration, I guess, or that you could, that was isomorphic to a graph that you could, that you were just looking at with no context, then what would you say the minimum weight was?
Well, there is no context here, right?
Right, so I see the point. So again, I guess the idea is that weight could mean whatever you want it to mean. So in the example of the graph, weight means cost of building a road. But for example, you could do this in a linear matroid. So a linear matroid consists of a bunch of vectors. And you might be interested in finding the collection of the basis which is minimum according to the sum of the weights of the vectors, which is the example that you're suggesting. And what this is going to tell me is I can use exactly the same strategy and that is going to work. So I could use this for any matroid and for any weight function that I can think of, such that the weight of a basis is the sum of the weights of the elements.
So there's another spanning tree there that would have the same cost to build all the roads? Or is that the unique spanning tree that has that minimum cost?
No, it's not unique.
So far I haven't said there's a unique one, and in this case there might not be a unique one. Is there a unique one?
Probably not, because there's so many duplicate weights.
It actually, it looks to me like this one happens to be unique, but that's luck. And in general, there might be several possible minimum spanning trees.
And also, from any one vertex, you're supposed to take the most efficient route, right? But what happens if you get to a vertex where it's the same cost to go either direction? So there's no logical choice.
So really what your question boils down to is this. I said add to I an element of minimum weight. But I said an element, meaning that there might be several. Okay? And so I'm claiming two things. The first thing I'm claiming is that regardless of which one you choose here, that is going to give you a minimum basis. Not the unique one, because there isn't necessarily a unique one. But if you follow this prescription, you're always going to get a basis of minimum weight. And there is another thing that we'll claim later, which is that actually, using this one algorithm, you can find every possible minimum weight basis. You just have to do it in all the possible ways of choosing the cheapest element at each point in time. Just deep?
Is there a situation where we're not looking for the minimum weight, but maybe the maximum?
So it very well could be. Sometimes you care about the basis of maximum weight instead of minimum weight, and of course you can probably imagine that it's the same thing, and you can just do the greedy algorithm, but pick the maximum available thing, and that'll work. And
you can map the weights to the maximum minus or everything versus distance from the max or something like that.
Right. I mean the proof is exactly the same. Okay. So this is my theorem. Question?
This is sort of back to Curtis's question. That at each step, though, you're not choosing from each vertex the best choice. You're choosing from the whole set of edges the best choice at each step. So you're not looking locally sort of on the graph.
Looking locally.
You're looking locally, as in at this stage of the graph, what's the next best vertex out of all, next best edge out of all the edges to pick? Not from this vertex, what's the next best one to pick? So that's why he picked, that's how he knew which 4 to pick, essentially. I mean, sort of, he didn't pick that 4 because he'd already chosen the 3. Does that make sense?
Yeah, that's a very good point. I mean, when I say the word locally, I mean locally in terms of time. At a certain amount of time, it seems like the best thing to do is to build the next cheapest road available. There might be several choices. So you saw, for example, when I built the 2s, I could have built this one first, I could have built this one first. It doesn't matter. You just look in the graph. Anywhere in the graph you find a cheapest edge, and you see if you can add it. If you didn't close any cycles, then you add it. That's the greedy algorithm. Okay, so let's go ahead and prove this. How are we going to prove it? We're going to prove it by contradiction. So assume that the greedy algorithm gave you this, gave you the basis I1 up to IN. And let's say that the algorithm chose them in that order. So I1 was the cheapest one, the first thing that was chosen. I2 was the next one that you chose. and so on until In was the last one that you chose. And because you're choosing them in order from cheaper to more expensive, if the order that you chose them is I1 up to In, then that's also the order of the weights. So let's say that's what you ran the algorithm, and this is the basis that it returned. I want to claim that this is the cheapest possible basis, so let's assume that it's not. Let's assume that there is a cheaper one. So assume that, let me call it C, J1 up to Jn is cheaper.
Does it, every time you do that, do you always have to have n rows?
Yeah, because every basis is equal cardinal.
So remember that, so the question is, why am I using the same n here? And the answer is that the theorem that we proved last time, that bases have the same size.
Oh, that's right.
And I need that. So let's say that this is another basis which is cheaper. It's cheaper. So what that means is the weight of the basis C is less than the weight of the basis B. And I'm going to reach a contradiction. Now, I can choose to order J1 up to Jn in whatever order. I'm going to number them in increasing order of weight also. So I'm going to assume that J1 is the cheapest guy in this basis. J2 is the next cheapest one in this basis. And Jn is the most expensive element of that basis. Okay. So I have B, I have C, and I'm assuming that C is cheaper, and that means that the weight of J1 plus ... up to the weight of Jn is less than the weight of I1 plus ... up to the weight of In. Okay? Now, if this sum is less than this sum, then there must be one term here and corresponding term here such that this one is less than this one. What do I mean by that? I mean, either the first one here is less than the first one here, or the second one here is less than the second one here, or so on. Because if it wasn't the case, then it would be impossible for this to hold. Yeah. So there, I can find some index, let's say J sub R less than I sub R. That must be the case. I'm not going to even assume that R is minimal. I just know that at least one of them exists. Okay? So now let's think about this. Look at the set from I1 up to IR minus 1. That set is independent, right? Because it is a subset of I. In fact, you know it's independent because this is the set that you get after R minus 1 steps of the algorithm. First element that you choose, second element that you choose. This is what you have after R minus 1 steps of the algorithm, and the algorithm always chooses independent things. So this is an independent set. And if you look at the set J1 up to J sub R, then that is also independent because it is a subset of J.
You mean C?
Sorry, of C. So this guy is a subset of B, and therefore it's independent. And this guy is a subset of C, and therefore it's independent. What do we do when we have two independent sets of a different size? We use the exchange axiom. It says, here I have an independent set, here I have a bigger independent set, so I can use the exchange axiom. The exchange axiom says I can find I1, sorry, I can find some j sub s, let's say, which is one of these guys, and I can add it to this one, such that I1 up to IR minus 1, comma j sub s is independent. This j sub s is in this list. So S is one of these labels from 1 to R. Okay. So by the exchange axiom, I found this independent set. Okay. Now, what can you tell me about the weight? The weight of this element Js. Well, these guys are ordered in ascending order of weight. So the largest weight that this guy could have is the weight of the last one, J sub R. Okay? But I assume that J sub R is lighter than I sub R. Okay? And therefore, J sub S is lighter than I sub R. Okay?
So you should have.
But look at what this greedy algorithm did. We goofed here. I mean, you had the set I1, I2 up to IR minus 1, and now in the next step we were supposed to find the cheapest available element. And we chose I sub R, but we had J sub S available, which was cheaper and preserved independence. So I shouldn't have chosen. I should have chosen or in other words, not the greedy algorithm. Would have chosen J sub S instead of I sub R. Here's my contradiction. Okay. And that's the proof. That's the proof that the greedy algorithm works for matroids. Any questions about that proof?
Contradiction is that you correctly use the greedy algorithm, the assumption that you correctly use.
Right. The contradiction is that I assumed that the greedy algorithm chose these guys, and then I showed that that's no greedy algorithm. It didn't do the greedy thing at step R minus 1. Because I assumed that it chose I sub R at the rth step, but it shouldn't have. It should have chosen J sub S. So what I used is not the greedy algorithm. Let me make 2 more comments about this. Okay? So comment 1 is precisely the answer to Curtis's question, which is what happens if you have several bases of minimum weight. The possible outcomes of the greedy algorithm are all the bases of minimum weight. We saw that there is some choice in the greedy algorithm. Sometimes you have 2 different alternatives to choose from. If you have the patience to run the greedy algorithm in every possible way, you are going to obtain all the bases of minimum weight, not just one. And let me make another comment, which is even more interesting. I told you that greedy algorithms sometimes work and sometimes they don't work. Sometimes the locally optimal decisions give you a globally optimal decision, and sometimes not. Okay? And so the question you might ask yourselves is, when does the greedy algorithm work and when does it not work? When do I use it? Well, the answer is that it exactly works on matroids. And it exactly doesn't work on anything that is not a matroid. And so if you want to define matroids in a new way, you can say matroids are the gadgets where you can apply the greedy algorithm. So matroids are exactly the, I'm going to use a big word here. Matroids are exactly the, for now let me say gadgets, and I'll say exactly what I mean by that. Matroids are exactly the gadgets where the greedy algorithm always works. What do I mean by gadgets? I mean the set systems that satisfy the first two axioms of independence. These are called simplicial complexes. A simplicial complex is basically one of these guys, EI, that we have, where you demand the first two conditions but not the third one, such that I1 and I2 hold. And if you, I think you, probably many of you have heard this word simplicial complex. It's one of the most fundamental objects in mathematics. If you want to know which simplicial complexes you can use the greedy algorithm in, they are precisely the matrix. Question?
Don't people usually say abstract simplicial complex when they state that definition in that?
Some people, not everybody. Some people call this an abstract simplicial complex, and some people just call it a simplicial complex. This is proved in the notes.
Axiom 3,
I'm sorry?
just Axiom 1 and Axiom 2, not Axiom 3?
In other words, remember, we felt like Axiom 3 was a little bit strange. I mean, 1 and 2 were completely obvious that independence should satisfy that. 3 wasn't so natural, perhaps. Well, this is showing that Axiom 3 is exactly equivalent to the greedy algorithm working. And so this might be a good justification for why